Okay, now we are back from the break. Before leaving you to Alexandro wise words for winning over Good Can Jam over and over again, two things I have to remember you very quickly. On our main site, Europython.eu, you will find on the red bar a menu. The fourth voice says this mobile guide. You go there, download the guidebook app if you didn't, and then you vote and rank this talk very highly, I suggest. No? Okay. Well, the other thing, this evening, starting at 9 p.m., we have a pie barbecue, so you can attend it if you're ready about the ticket. Otherwise, few are still being sold. So, okay. Now, Alessandro.
Thank you. So, after the break, we talked a little bit about the solution of store credit and the idea to solve it in some nicer way. Now I want to wrap up the conversation because I think it's very general. I mean, what happened is very general. The guy here said it's possible to do it faster. Sure. Using a mapping. And there are ways to do that with the mapping. The point is, after a while, one of the other people here noticed that the solution we thought had a corner case that you had to treat independently. I mean, you should put an if somewhere that for that corner case and check that it and treat it differently from the usual mapping stuff. Would be the case in which you have two items with the same price, but your credit is exactly twice the price of these items. Why? Because we know that since it's unique, two items with the same price could be skipped, but not in that particular case. So this is the problem with a lot of optimizations. You might not see immediately all corner cases. So one of the main advantages of PyPy is that if you have the chance to do the most trivial thing, the certainly correct one, and it you leave the optimization to PyPy and it usually works, then you should go for it. Why? Because in this way you don't need to think about special corner cases that no, otherwise you have to care. Actually, even if you think to all the corner cases, sometimes at the implementation level, when you specify the corner cases, you put ifs or something like this, and it's one more line of code, one more point where you can do a mistake. This is very important. Probably a lot of people that program in Python already know that if you don't overdo in being concise is better because it means you have less places where you can get it wrong. And especially don't put stuff that it's not completely needed. This is even more important here in coding competitions because every single bug, it means you're losing a lot of points, a lot of positions. If you have to start, look at your code, and it's not obvious what is wrong, it will be a lot of time with respect to, I mean, anyhow, you are going to have 40 minutes to 1 hour for each problem. So if you spend 5 minutes with a single, the bug session, it's a lot of time. It's more than 10% of the time that you allocated to that problem. So always go for the obvious. This is something that I tried to put in the various solutions. They are not the most clever, but usually the simpler implementation that I could think. So now I would just have a look at the last one of the simple, of the three problems in the code gem that we saw. We saw store credits, reverse words, and this one is the toughest one, T9 spelling. Now, if you read the problem statement, that just click on the previous page, and it's basically you will be given a string of text, and you have to convert it into T9. That is, you have to press numbers like in the old phones, so that you have, for example, 2 correspond to A, 2 correspond to B, and 2 correspond to C, and etc. Now, this is just to see. This one, it's not complicated from the point of view of the algorithm. You have just to code what they ask for. There are a few of there are not very much. There are only these kind of problems. There are just implementation problems. Are not many because it's there's not much fun. You have just to code fast. You don't have to think much, but it happens to have them. And sometimes the trickery to get all the cases correct makes a good problem. In this case, what I want to show you is that one of the trick I used is I need a conversion. Basically, I want to convert every character in the input string in a substring, in a non-substring. So I want to use the string 2 for A, 2 for B, etc. But since it's very long to write that conversion string, the mapping, I use the following trick. I wrote the simplest inverse. I basically say that A, B, C are the 3 letters that are on 2. D, A, F is the 3 letters that are on top of 3, etc. Then I did I built the reverse mapping from text. I don't know what is T and R from. Okay, it's T9 reversed and T9. So I get one after the other those ones, and I write for every letter the corresponding sequence of numbers. This way, I have to write 3 lines of code that are easy enough, and those are faster to type with respect to the other. The other is much longer because you have to type a lot of many more characters, and you have to, somehow to double check more. You just have to you have the image here that tells you what are the numbers for each letter. Anyway, after that, it's pretty trivial. The most important point is to notice here. I get a line, and then I skip only the return. Strip usually strips also initial, leading, and trailing spaces. This is not what I want. In the statement, they say that there will be leading and trailing spaces, or not. I'm not sure if they say, but they didn't say that it won't be there. And since the space is one of the characters that is possible to use, I wanted to be sure. You need to think, not to do the input in your usual way, which would be with strip. Then you just get the new. Okay, I use the tricky part is here that you have to insert spaces when you have 2 consecutive letters that have the same that are on the same key, and this is Do you remember? You have to say, if you want to say A, B, you have to type 2, then wait, and then 2, 2 to say the B, otherwise would seem the C. So since I knew I had to to check for the previous letter, I initialized the new string with outside of the loop. In this way, I don't have to care inside the loop not to have not to have the previous line, the previous character already set. So here, basically, what I do is I just try to put the next string of numbers, and if I find that the same number is in the last character in my output string, I put the space and then I add it. Now, this is a typical implementation problem. It's trivial to do, but you have to try to minimize the places, the corner cases where you can get in trouble, just forgetting small details. Now, right now, let's say this was in order to get all the problems didn't pose any problem from the computational point of view. It's just to get started so that you have all the input, output, and everything. You know what is the style that you should use. Now, if you go to snapper chain, you may, obviously this link, it's horrible, so you should just look for Google Code Jam snapper chain. Which is what I will do as well. So, now, just look at have a read at the statement. Usually the statements, especially in the code gem, are somehow fancier than the usual description of a problem. It's not just you have a set of numbers and you want to switch something and so on, but they always try to put a story around it. This is nice, it's a bit distracting, and you have to be used to read the problem statements this way. It's their trademark, and it's actually, I liked it at the beginning, and I like it even now, but sometimes I find a little bit too confusing the fact that there is all the story around. Anyway, it's the same for all the compilers, so it's... So basically, these are strange devices. Every device is either powered or not, and it could be on or not. And there's a way you switch on and off the power on the first device. They are chained, and so the pattern of what is on and what is off will change in switching again and again and again. Now, what I'm interested here, it's just now, what I'm interested in is, what are the numbers here? Basically, you have up to 30 snappers, and you can do on and off up to 10 to the 8th times for the large input. Obviously, the small input, it's trivial. You can do it however you want because k is just 100. So, but this one, it's 10 to the 8. So for the first time, we actually should care about if this stuff it's doable or not. So the first trivial solution is just implementation would be to switch the first time light and then see what happens to the device, to the snappers. The first one will be on, and then the second is off. Then switch off again. Then the first one would switch off, and then the other would go on. So there is a process, and for every process, you have to, for every test case, the complexity of your problem is more or less the number of devices times the number of time I switch on and off. That is, in every test case, I will do on and off, and on every on and off, I have to check the whole list of devices to know what happens to every device. What is strange here is that t is very high. It's 10 to the 5. Usually the number of test cases is like 100 or 1,000, but these are 10,000 test cases. And the reason is that you do 10,000 by 30 by 10 to the 8. There is the maximum number of times that I can do on and off at the plug. You end up with approximately 10 to the 14. Now, 10 to the 14 is a number that is a problem. That is, the number of operations, you don't know how long is a single operation, but the number of operations is so high that most probably you're not going to do it on your laptop. Or, what is the upper computational limit of your machine? Now, here I have my calculation. Try to do it first by yourself. What is the maximum number of operations, whatever operation means, but let's assume you have some simple operation. What is the maximum number of operations that you can do on your machine within 8 minutes? How will you do? So you have some gigahertz, that is the clock. It's 1 over time. It's the number of operations that you can do in 1 minute, in 1 second, and then you have the number of seconds that in 8 minutes. And if you parallel your stuff, you might have multiplied that for the number of cores. The number I use it's like something like 2 gigahertz. That is 2 to the 10 to the power 9. 8 minutes, it's approximately 480. So very roughly, 2 gigahertz for 8 minutes, it's approximately 10 to the 12. So anything that is higher than 10 to the 12, it's not going to be done on a single core on your machine. If you manage to split your problem and use 2 cores, you can go just above it because it's a 2, and here you are fighting with powers of 10. But then operations usually are not that simple. I mean, the single for loops will not be just done in a clock, in a CPU clock. So usually, I mean, as a rule of thumb, what I think is that 10 to the 10 is more or less the limit that you are going to use. You might think that something, I mean, if you know that the last 4 it's very tight, you might try to see if you can get to 10 to the 11th, but it's really, you start to get really close to the limit. And you always have to remember that you have a number of test cases. So even if n by k would be fine, because would be 10 to the 9th, so actually doable, you can do a single test case, but you can't do 10 to the 5 test cases. So that is one of the limits that actually I was beaten a couple of times by the fact that I didn't notice that there were a lot of test cases. And but that enters into your big O notation computation. So just keep in mind, 10 to the 10 is more or less fine. Or, well, I mean, it's your limit. If you are below, fine. If you are above, you're in trouble. 10 to the 10, you have to actually profile your code to see if it works. Then, in order to solve the problem, there is one very usual trick. You have a certain sequence of the snappers, and then they give you 10 to the 5th test cases. But since the snapper are 30, I mean, all the snappers start on off. So you have the only input is the length of the snapper chain. So you don't have really 10 to the 5 test cases. You have only 30 because you have length 1, 2, 3, 4, and they will just repeat and ask you for length 5 several times. So you could just pre-compute the solution for all the 30, and or actually you can get not pre-compute, but cache the result, and so you have much smaller number. Then actually, you may use another trick, that is to notice that you have 30, at most 30 snappers that can be on or off. So they actually can be within an integer. So if you can think of it as bits in an integer of 32 bits. And if you happen to think about that, you may notice that the way it works, it's actually every time you switch it, you get XOR operation on the integer that you were having. So it's actually a repeated XOR. So you can do the whole snapper chain with just one very fast operation for every time you switch on and off. So you start with 0, and you can go on and on and on and see what applying the same fast operation again. But then there is one more trick, actually, and this you have to start with one of the test cases and see how it works, and how this quite often is useful to see how the process evolves as you do some kind of loop. And we may notice that the integer that you're using to represent the snapper chain is actually adding 1 every time. The problem is actually just summing all the number, summing up to a certain, up to k. So if you could stop at various levels here and still get the problem right, but the solution, it's really trivial once you see all the tricks that have been used in giving the solution. Basically, you had to get your the length of the snapper chain. 2 to the n is it's the number where all the snappers are on, and it's the only case where the last one is on. And then if k it's divisible, it's divided by s, it's has the last bit on, then it's on, otherwise it's off. So in this case, you have you start with something that looks very large. You have to see that only some of this happens more than once. The fact that the number of test cases is overabundant, so they will repeat that. If you see that the space is smaller, the space of the solution is smaller than the number of test cases, you can actually solve all the problems, all the possible problems and then just match the solution with the test case. But in this case, you have several more tricks that you can use up to the level where the problem becomes a simple two simple operations. Now, I mean, each of the problem, if you want to understand it fully, you need to spend a little bit of time, especially, I mean, the first ones were really easy. Now it starts to be, I mean, at least interesting. And if you want all the steps, just go to the context analysis, which is, here we have snapper chain, context analysis, and then problem A. And this is the solution. It explains how the solution works. Now, this one, it's another very interesting problem. And here you start to see, I mean, what a real problem is. This was given in round 1B. So it starts to be, I mean, it's not qualification round where they give always something easy enough that everybody can do, or at least during the qualification round, you have 24 hours to do at least one of the problems, and you have 4 problems. So usually the qualification round, it's quite easy. And round 1 starts to be tough because problems are tougher. I mean, you have to actually find a way to solve them, and only the best 1,000 competitions go to round 2. So you are not just, it's not enough that you solve some problems, but you have to solve enough problems and fast enough so that you are in the top 1,000. Now, let's go to the problem statement. It's a bit longer. You should read it quite with care. And what happens is basically that, I mean, it's you are in a kind of a maze. You can move from every place where you are. You can move only in certain directions, and how fast you can move depends on various conditions. You want to get out, and there is also a time dependence. It's also conditions change with time. There is the high tide is going up, so you can only move when the tide is high enough, and you can't move when it's too high. So basically, you have a grid of possible positions. You have, for every point in the grid, you can move in certain direction, but the speed of the movement and if you can actually then do the movement depends on time. And they ask something very simple. Try to get out as fast as possible. If you want to, I think it's better if you read it for yourself. I'll do as well, just to refresh the... But then we don't have time to go into details with every problem. But in this case, what I'm interested in seeing what is the steps to understand the solutions. So don't try to understand just don't try to find the solution, but just to see where are the conditions. So the problem looks like this. You have a maze, that is, you know where you can, you have a grid, you can move from one point to one node of the grid to the other, and you have a description of in which direction you can go. But then you have water that is decreasing. Water decreasing, it means it stops some of the way, and it influences the speed that you can do when you move from one point to the other. Since the water is decreasing, the fastest route that you are looking at, you are trying to find, actually it depends on when you get to every point. Now, since this is a shortest path problem, you need to escape the cave in the shortest time, but this is actually the shortest path because you can consider not just the distance but the time you spend as a measure of the length of the path. So there are algorithms to do the shortest path. The most known algorithm to do shortest path from 2 points is the Jastra algorithm. But Jastra algorithm doesn't depend on time. I mean, you have a graph. This is a maze. A maze can be transformed into a graph where nodes are places where you can be, and edges are how can you go from one node to another. Permissible, available node directions are edges. Now, Jastra usually, but you don't have fixed weights. You have weights that depends on time. So how do you modify Jastra, the standard algorithm, to use it? I mean, is it possible? The amazing answer is yes. I mean, it's a complex algorithm, but you can actually put in something that was not thought, that is time dependence, into the solution. So you don't have a graph. You can't draw the initial graph, but you have to modify the algorithm not to work on a graph, but to work on a grid. And you will plug what happens with time inside the weights will be, produced on the flight instead of given at the beginning. Now, let's see the various steps. First input is this one. You just read the integers, then you read the two maps that describes the cave. They are just integers. Then you start with the distance in time from every point in the cave. The idea is if you find the fastest route to a certain point, then the fastest route moving from that point to the other, the point would go through that one. So the idea is to find the fastest route to all the points. This is the Jastra algorithm. You start from a point and then you look for the shortest path to all the neighbors and then to the shortest path to all the neighbors of the neighbors, and then so on and so on. And at some point, when you hit the exit, you say, OK, I found the shortest path in the exit. So I set up a table with the shortest path, and I put it a very large numbers. And that means I didn't find yet the shortest path to this point. T00, it's the initial position, so it's just 0. It's I'm there at the beginning, so the distance is 0. Then I define my state. I am at time 0, at time t00, which is 0. Oops. And I'm at the initial point. Now, what I do here, F is a list. I will add to this list all the nodes that I explore. So I look for all neighbors, and then I will put all the neighbors into F, so that I will check, after I check the first position, I will check all the neighbors, and then as soon as I discover other neighbors, I go on and add them to this list. The trick is to use the heap queue data structure, which is a partially ordered list. If I add items to the heap queue with the heap push method, what I have is that the list is kept in partial order very fast, and whenever I get the heap pop, that is, I pop the first element from the list, I get the element with lower t, that is, the shortest, the first position that I didn't explore yet, and it's the closer to the initial point. This is the Jastra algorithm, and if you look at if you want to see a clean implementation of the Jastra algorithm, it was in the recipe at the beginning. Now, what you do is that you look for next closer, then next closer, then next closer. You see if you arrived. N-1 and N-1 are the exit points. So if you arrived, you are arrived, and you can safely say that T-1 is the time that it took, the optimal time that it took to get out. Otherwise, you look at all the neighbors, and this is the complex implementation of all the details that are explained there. I have to check if I can go there, and that is, I get the minimum of the starting point and ending point, and the high ceiling of where I am and where I want to go, the low ceiling of where I am, where I want to go, and if it's below 50, I cannot go. And then I get this one, I don't remember the details. This one should be it's time. Oh, I don't remember the details. Anyway, here you have to describe the rules that they gave in the problem. You have, let's say, this part, start, heap pop, and heap push, that are basically the Jastra algorithms. You look for neighbors. Then here you have something that is complex. It's not usually part of the Jastra, because this stuff it's specifically designed by them to not be a simple graph. But you can tell every time you find the shortest path to a point what would be the shortest path to go to the neighbors. You might have a different route, and so if you have to think, if you found a different route that is fastest, then you will get the other route. Now, the takeaway lesson here is you need to know how to do the algorithm that is just look at neighbors and then look at next neighbors and next neighbors and keep the list of neighbors to be checked ordered or partially ordered in this case, which is much faster than ordered. And you can do it in Python with heap queue, which is a data structure that is extremely useful. It appears quite often. And then be ready to get the standard algorithm and put inside the infrastructure that you need to have something different. Here, the modification is that it's not a graph, but you have to build the neighbors on the fly, and you don't have weights, but you have to, since you know at what time you arrived, you know what is the height of the tide, and then you can build at that time the weight, that is the time that it takes to go to the other places, to the neighbors. So the point is, if you don't know that this is a shortest path algorithm, and you have a complex set of rules or how to move, but you miss what is the correct steps that you have to do. You may just try to look for all possibilities. You may start to look for all possible paths and see what the path would take, and that is extremely expensive, because the idea of Jastra, which is very general, is to use the knowledge of a piece of the solution to get to the next piece of the solution. Since once you found the shortest path to a certain area, you can explore and look for the shortest path of the neighbors of that area. This happens very often, that you have to reduce your problem to the same problem that is smaller, and then work on the border. Now, what I wanted to show is a different problem that comes from the competition of yesterday. That is problem C. It's the only one that I did decently. The competition is found here. Unfortunately, it's not. They don't give the test input, the test data set, so you can only read the problem statements without the chance to test it. So, yes?
For streaming purpose, if you can type enlarge on your monitor better.
You're sure? Yes. This one is it's
slash 3Q7 Z, small z, capital N.
sorry.
Great, thank you.
So this is the set of problems that they gave us yesterday. Now this one it's pretty easy to read, so you can just read it yourself. Basically, they have a league. In this league you have pairs of competitors that are fighting, and so they are troublesome. And once you have all the, you want to find to split this league in two leagues where nobody is fighting. That is, put everybody, all the fighting couples in different leagues. So if you strip the story, this is basically, you have two sets and couples of, you have one set and you have a list of couples from elements of this set, and you want to know if it's possible to separate two sets where no couple is in the same set. Sorry?
Yeah, I think if you didn't register, you can't access the question.
Ah, you don't see it? Okay, yes, because I'm still connected. Oh. Anyway, this is rather easy. And they don't give you the possibility to download the input, so we can just read it here. Now, if you don't know where to, I mean, what the solution would look like, you would think that it's not such a tough problem. I mean, you just start with put someone in the one set, and then get everybody that is fighting with him on the other set, and then start to trying to put people here and there. What happens is that you have actually a lot of choices. So depending on how big your input dataset is, you have to keep track of all the tests that you did, and if it didn't work because somehow at the end you couldn't separate all the couples, all the fighting couples, you have to go to the next try. So this is actually a known problem in graph theory. It doesn't look at it. It doesn't look like a graph theory problem here, but actually, if you notice that these are pairs and you want to separate in two sets, this is something that is a bipartite graph. You should know it. It's not something that you get that you can think during a competition. Also because it's difficult, even if you try to look for something interesting in Google, it's not easy to get the proper keywords to get. I already did a problem like this, and I watched the solution. I mean, I watched the contest analysis and where they explain everything, so that yesterday when I saw it, I said, okay, this is a bipartite. Then I went to Google looking for bipartite, and it worked. Okay, yes, it really looks like it's a bipartite problem. So I went to NetworkX docs. NetworkX is one of the libraries we've installed, and I just looked for bipartite. Where are you? It's in the reference. reference. So they have a module, and they have this nice function that is just is bipartite. Now, once you know what the problem is, or once you get a ring of something that you know, you can find a way to get information from the internet, double check that what you're looking at, it's actually the kind of problem that you thought. You have also ways to, to be sure that it's like this. And if you know where to look, some of the problems are trivial. The solution for this one now, don't look at all the rest. It's all craziness. The solution is this. Basically, yes? So one of the tricks that I use is to use always very short letters, and I also shorten all the libraries that I use. So I have all the imports pre-written in my template code, and I just remove the comment where I need it, and so network X is netnx. I instantiate a graph. Then they gave me a line with two strings that I already separated in two tokens. So this S is a list of pair of strings, list of tuples, and each tuple have exactly two strings. So I just get first and second, and I add an edge to the graph. This is all you need to produce a graph. Actually, in Network X, a graph, it's a it's a nice data structure because it doesn't ask you to have some node class or something fancy. Any Python object can be a node. And if you add an edge between two nodes, it just creates the nodes, and then it connects them with an edge. So you don't have, it's very easy to, and very general to create graphs. Once I did that, the solution is just to ask bipartite, is this graph bipartite? Because it could be done or it could not be done. Solution, and then if res yes, else no, you always double check several times that you actually spell correctly what they ask for the solution. It happens quite often that they ask for a number, or if it's not possible to have a solution, to write a specific sentence like impossible or oh, we failed or something like this. And so you have to be ready to do something to translate your solution into the proper string. Now, without this, you are in for a lot of coding, trying to find some brute force approach that maybe takes 10 minutes to do the large stuff. But the sequence is study, recognize something that's similar to what you have known, double check that it actually is what you thought. Usually just looking for the internet, on the internet it works. A lot of stuff from Wikipedia are fair. I mean, you can get enough information. Not everything. There are some of the advanced stuff that are that they use in competitions that are not as good in Wikipedia as you would like. And then after, if you know something, you also know where to look for a solution. You have to get this link between theory, model, library that solved the model. If I don't have the library, I go around the internet and cut and paste something, and then if I like it, I put it into my into my library, in my own library. For example, this is a quick look at the library that I usually use. There are a number of things that I found useful in various competitions. One is, can you read it with the red stuff, or Daniel, sorry, is it possible to turn the lights off, this one? Because yes, unfortunately it's red. Anyway, there are various ways to do all the okay. So GCD is the greatest common divisor. Now it looks something simple. Actually, you can get it also from I think PyPy or something. But since it's a very simple algorithm, and you most probably are going to use PyPy, so you don't care if it's a recursive. So it can be slow if you have to do with something really big, but it's not really a problem usually. And this way you have complete control of what you are using. LCM is exactly as it uses its least common multiple and greatest common divisor. And these happen I mean, they're very useful. They happen all the time. I happen all the time to use this. For example, if they ask you the direction of something and you have the vector, you need the common divisor in order to get the least, in an integer stuff, you may have several vectors that have the same direction, but if you get the least common divisor, you have only one vector. I mean, you divide by the least common divisor of the two, and you can identify the direction. So there are a lot of cases in which that looks like very esoteric number theory stuff are very useful. Actually, there are also a lot of problems that ask explicitly for greatest common divisor and stuff like this. This is the binomial. It's very, very nice, and I actually copied it from integrating what I found in the source code of two of the really good competitors. I don't remember exactly. Okay, the reason is the binomial is needed for really large. I mean, this is able to give numbers correctly even for very large numbers, and R can be very large. This happened to be in one of the code jam recently, where you had to build a binomial, but since the binomial it's a formula that you can find in libraries, but libraries usually can handle only up to a certain number. That could be probably 100 or something. And they explicitly put in one of the test cases there was a huge number up to 1,000 that was not the usual libraries, or a simple implementation would fail because it was going above the limit for the functions. Something that I found amazingly useful is the integer square root. This also is quite crazy, and the idea is this. You need quite often to do a square root of something. The square root gives you a float. So if you are handling very large numbers, when you get a float, you only get the beginning of the square root, and then you lose all the decimals beyond the 16th or something. So even if you want to do the square root of an integer, you still have to go through floats and then back to integers. let's see, I don't remember what is the limit, but probably if we do 2 to the 64, sorry, to the 64, import mat, root of 2 to the 64. Okay, it's not enough. Okay, now I lost significant digits. Let's do int. It's like this. Now let's try to import lib. So it was 228. Okay, it's still correct. So let's go one more. Int too large to convert to float. So just doing the square root of something, of an integer, is something that might need a specific function. And this is nice because if you look at the code in active state, you should look for I square root or integer square root in active state, in the active state recipes. And they say that there are a lot of implementation on the internet that are incorrect, that make a mistake of one, I mean, in a few corner cases. Instead, this one is more, I mean, they tested this against the others, and that one was this. They at least claim this is the correct one with respect to the others. And this is my Jastra and heap queue implementation. So you have to do something like this. This get the nice thing that the nice and general thing, you spend a little bit more time, you polish it a little bit, and store it somewhere. And you can get it when you need it. I think, no. Okay. One of the Google Code Jam was just applying the repeated greatest common divisor to a set of numbers. And if you had the good function of large numbers, if you have the good function and you knew that you can compose greatest common divisor, it was just a matter of doing the for and getting the right function. So lesson learned. Once you go into the above the very easy code jam, what you are facing is stuff like this. That is, you certainly need to know an algorithm, but then you have to do a lot of tiny little details. Those tiny little details is not something that you can capture with some high-level API like NumPy or something. This is not a multiplication of matrices. You cannot just sum to arrays or something. You need to get low-level that compare that item in the array with the other item in the array, and sometimes you say, okay, if maybe it's with 2 items and so on. And all this stuff needs to be done at a very low level, at least. You want to be able to do both upper level, like I take something and then sort it, and I don't want to know how to do the sort because sort algorithm is good enough. Or if I need to do a subtraction of two matrices or two arrays, I just use NumPy and it works and everything is fine. But at some point, all of the interesting problems will have you go into the get the index of the array and some 3 and something like this. So you need to program both at higher level and be able to go to the lower level whenever you need. The point with PyPy is that you can do this without caring about the fact that you should micro-optimize lower level operations. Actually, one of the advantages with PyPy is that you may even forget about a lot of micro optimization that you usually do. For example, something that I had in the other presentation is that in a longer competition, I had to divide, to do various operations and divide by the size of the array of the list I was operating on. In Python, since it was within a for cycle, in usual Python, I should micro-optimize the fact that I need to do to measure the length before starting the for loops. Otherwise, I would call len 1,000 times. Instead, with PyPy, you just don't care, because once the warm-up cycle has finished and the JIT notice that you are doing something within the loop which really could be done out of the loop, it does automatically. So with respect to easiness, code simplicity, you may even forget about some of the lower level optimization that you would do usually with Python, with CPython. So you get a double advantage of using PyPy. From one point, it's easier to grasp your problem because you don't need to, you're not forced to use higher level programming, but you can also go lower level without, fearing too much of a hit. And you can even skip some of the micro optimization. So your code must look much simpler in PyPy. If it doesn't, it means that you are not leveraging all the advantage. Then there is also another point, that simple code, if you write your code in a stupid way, you write if this, if that, if that. If you have actually 3 conditions, you just put them one after the other, and the JIT understands better what you are doing, instead of doing some kind of fancy stuff like multiple or trying to be clever to do less calculation. No, it's not. If you even if your code is simple to read and to translate to what it's doing, it means that the just-in-time compiler will be able to optimize it better than something that is more complex. This, by the way, makes also your debugging time go down, because when you have something like this, if you have a bug anywhere here, I don't remember how long it took me to do this. I suppose probably an hour and a half at least, probably a couple of hours. And actually, once you understand the problem, it's easier than it seems, but still you can make a lot of mistakes. Just put double I here or whatever. Actually, yesterday I did a really cool mistake. I was having, I had already tested everything was working. Then I said, okay, maybe I can I should make this a float. So I use v. I mean, instead of having v as a pair of integer, I use v equal to map, float, comma, and then the wrong variable. It was something else. And then suddenly nothing was working because I just was looking for, I completely destroyed the stuff. And if you're doing something complex, once you have problems, you have to look in more places. I mean, this one, it's horrible, but you can't do anything less than this. It's the problem that is correct. This one was quite a tough problem because there were a lot of details. But if you had to do with something like NumPy, you should have done an additional level of complexity because you have to decide how to slice and so on. So in the end, the main point is, if you want to be successful at coding competition, you need practice. Practice means learning. Actually, I show you how to download stuff from the Google Code Jam, that is from the competitors. Usually, there is another, okay, I forgot it. There is another very important resource if you are doing Google Code Jam, that is GoHero. GoHero.net, absolutely find this, use this link. Now, this is a website done by one of the competitors, so an amateur, that downloaded all the solutions from the site, then analyzed that and decided what was the language, and then did some data mining on that, so that you can see how many people solve problem A using which language, or you can ask from regional stats. That is, for example, we can see how many participants were in the, yes? Oh. Okay, but I think not the bit.
Anyway, all of this will be available online, so you can look back if you like.
Yeah, but so do you see it now? So as you can see, in the qualification round, most of the contestants were from India, United States, China, Russia, Japan. Now there are some of the nations that have extremely great communities. That is, they are really strong. As you see, remaining these are the people who are in the final. So among the 840 Russians, actually 8 are in the final. So it's a huge number, especially judging from the fact that in the US there were 2,500 competitors, but just 3 are in the final. Actually, Italy is extremely bad. I mean, but really a lot depends on community. So if you like doing stuff like this, look if you have a local community, if there is someone in your area or at least in your nation that is doing this stuff, because obviously a lot of stuff can be done online. And for example, in Japan also has 2 competitors, but they are really, really strong. I mean, they could place at least 4 people in the final. And they were just, not competitive something like 5 years ago. And instead, now they are one of the best competitors. Also, Canada has good competitors. Poland is extremely strong, and usually there are a lot of people from East Europe and Australia, Canada, and so on. And it very much depends on how strong a community is and how much the coding competitions are valuable in the university curriculum, for example, which is very high in Russia. They care about it very much. There are also team competitions, and the Russian team is really strong. Actually, the two best competitors right now are Gennady Korokevich, and Petra, what's his name? Petra? Petra. Petr Mitrevich. And those are the two best. Gennady is from Belarus, exactly, and Petr is Russian. And actually, Petr Mitrichev is a Google employee, and he won the Facebook Hackers Cup for 2 years. So he went to get the cap, and to receive the cap with the Google badge. Here it was, everybody was saying, yeah, great. Here, this is his block. And
Gennady is 19.
yes, Gennady, how do you say, Korokevich? And basically, he was winning anything from, high school stuff to pro stuff, and at least once he could not go to the final in the Google Code Jam just because he was not 18. They had explicitly said that for the final you have to be eligible to go to the final, you should be above 18 years old. So
For the same reason he was banned in the top coder.
exactly.
He was too young. Finished a couple of years on the year.
Yes, and now it's number one on top coder. Yes, he's number one on top coder right now, Tourist. Yes, and he programs, I think, in some crazy language, right? Something like in D. Yes. Oh, he didn't do the... Let's see. So he's...
He used to win the International Olympiad in Pascal, I think.
Yeah,
Pascal, yes, exactly. He programs in Pascal. D is the programming language of one of the Japanese guys. D. I think that let's see, language popularity. Pascal. He's from Belarus, and so Gennady Korokevich. Oh no, now I started with doing C++. So this is really a great resource if you want to see who is doing what. And this is where you can see that, for example, this is the 2013 contest, and I showed, no, not Pascal, let's go to Python. This is where you learn a lot, and you can see what are the various solutions of the good players. And I think this one is the one that I was talking about. Be Merry, as you can see, is a C++ programmer, but then 30 minutes with 30 minutes left on the competition, he produced, okay, obviously I already have it. As you can see, I usually look at what other people do to learn, and I suggest you to do the same. This is 3.1. Okay, so GCD, as you see, something very useful. Whoa, and he used a lot of functions. This is crazy. Anyway, these functions probably are just stuff that he has in a library. I mean, you don't write functions during the compilation. And this is the solution. And I guess he switched to Python because he had really not enough time. He had just 30 minutes. There were people addressing the problem since 1 hour. So it was clear that it was tough, and they didn't manage. And so he went into the language that he is also fluent, and that probably he judges was faster to code, even if not as fast as C++. So absolutely go and see what others do. There are really crazy things that you can see. There is one of the competitors who upload the solution with a full stream of conscious on how he reached the solution. This is in the qualification round where you have a lot of time, so you can actually stay there and try to think, etc. And let's see if I'm finding, should be something buried. And treasure was the tough one. Let's see. Buried 3.1, save, replace. Open with. Now, here you have to upload the source code during the compilation, and this is the source code. So yes, nice comment with what it was, treasure, and then also we have to report the lexicographical smallest first order of chess necessary to unlock all of them, blah, 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 blah. Oh, but this is too big, no, we're not going to do it, and blah, 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 blah. I was really shocked when I saw this. And he solved the large problem, that was really tough. And okay, no, it was seriously, I'm thinking this must be the case. Because I really think my current algorithm is pretty nifty. I'm going to go straight to the large dataset now. If it's wrong, well, I've already spent a lot of time on this problem and I don't want to waste more time. I mean, he was there writing this before submitting.
Writing this in the contest?
Yes, during the contest. This is the solution that he uploaded as he won. I mean, he was one of the few that could submit problem D large. And this is all how he reached to the solution. It's amazing. I mean, I spent the evening just reading that and try to understand what was thinking. Obviously, be careful. This is in the qualification round. You have 24 hours, so it's different from any. If you have 2.5 hours, you're not going to write poems during the competition. Yes.
It probably helps to see the thinking process of yourself and see if you made any errors, because after like 2 hours thinking about it, you don't know anymore.
Absolutely. Absolutely. And it helps you, and especially because sometimes what you need to learn is where you made it, where you got it wrong. For example, I found last year the way I failed to the round 1 competition, the round 2 competition to go to round 3 was very, inspiring. Basically, I almost solved 2 problems, but then I solved none. And the problem was this. The first problem was, they asked they gave you a list of numbers and you have to do something within those numbers, and then for every number write a result. I got those numbers. I knew the solution was implied sorting them. I sorted them. Then I got the result, and then I wrote the result in sorted order instead of putting back instead of using the first order. And I was sure the code was correct, at least. The solution was correct, but the output was not. And I spent something like half an hour staring at the code and say it's correct, then writing tests to actually see that it was correct, but I didn't check the output. And yes?
No, last year, okay, I did a perfect solution, okay, for one dot at the end of the
Of the output?
yes. For one dot at the end of the output, it would give me all errors, and I was continuing to resubmit
Exactly.
for one dot. So
The other error was even more interesting because there was some kind of crazy stuff going on, and I said, okay, I think this could be done with the greedy algorithm. And I said, okay, this probably is a greedy algorithm. Greedy algorithm means that you have to do several steps of the solution, and at every step you have a way to get the optimal solution. So you build the complete optimal solution doing all optimal steps. That turned out not to be true, but very, very close to be true. You just needed to keep in mind that there were cases in which you needed to actually test also non-local optimal solutions. But I just forgot I did the assumption. I mean, I thought I only was looking for greedy algorithms, and I forgot that was an assumption that I did at some point without being sure it was correct. And so writing down what you are doing, or at least a debriefing after you do a competition, and you say, okay, I did this, and then I did this because of this. And after a while, you actually get better at planning what to do. Okay? For example, the way I qualified last year from round 1 to round 2 was quite telling. I started doing a problem and I couldn't. Then I went to the second problem and I noticed that people were already submitting solutions. So I said, I'm stuck on the first problem. The second problem doesn't have many points. So it's useless for me now to work on the second problem because anyway, people solving problem A and B, the easy ones, will be faster than me. So I went to problem C that looked crazy. So I started working on that and I analyzed that and I managed to do the small data set and I had some idea on the large data sets. I went back and there was no way to qualify unless I managed to solve the large data set that had a huge number that gave a huge number of points. So, I mean, it looked difficult and it had a huge number of points. So I said, okay, this is the only chance that I have. It's useless to do anything else. I mean, you have to start to think in competition way. I mean, you want to get to put your work to use. So it's useless to do something that will not bring you to the next round. And so I said, okay, now I've spent 10 more minutes studying this. If it works, I can go back to problem B and try to do that one. At the end of the 10 more minutes, I say, okay, I think I have the idea. I'm not sure it works, but right now I don't have other chances. So I coded something. Actually, I didn't code because I used the small solution, also for the large data set. Did a couple of tries, then submitted the large data set, and it worked. So and I was sure it worked. Even after I uploaded, I knew it. I mean, I didn't need to see the judge. I knew it was the kind of problem didn't need the judge to tell you if it was correct or right. The only point is that it could last too long to solve. Instead, it worked, and then after that I said, oh great, now I'm qualified. Now I really feel relaxed. Oh great, I went back to problem A and I solved it in 5 minutes because then I just say, okay, I'm relaxed and you have to, I mean, after a while, you have to start to think like this. What is the most effective stuff? Even if something seems crazy. I mean, it was the problem space looked something like 2 to the power of 500. So, and in principle, you should have looked at all of it. In practice, there was a trick that permits you to say, well, I will start looking for this immense space, and I will find a solution very early, much before I even start at a tiny bit of the space. And it actually worked. You could find a solution in a few seconds. And yesterday, for example, yesterday, the guy who won had the perfect strategy. There were 4 problems. The first were very easy. Everybody started with the first, and it was obvious that people were not, pro. So you could, if they managed to do that problem, you could manage as well. So I and also the first competitor went to the 2 last problems that gave a lot of points. I managed to solve the first, and then the second I said, oh, this is very long. It's trivial, but it's very long to code. So I'll try to do the second first, and then I'll go back here. And then I got stuck, and I failed miserably. Instead, the other guy went through the fourth, and at the very last, he managed to solve it because it was just long. It was not very difficult. And so he managed to solve only 2 problems, not much, but there were enough points to win, because everybody else was doing the easy problem that, okay, they was maybe a 15-minute work, but it was 15 minutes wasted because it was too low a value.
Sorry to interrupt you. Last 15 minutes also for us. If you have any question time, otherwise you can go on.
I think with exploring these resources, I think I finished. So if you have any questions or comments.
What was the name of that user again?
Barry D.
Barry D was the user.
Yes, it's this one. Also, the other solutions are very interesting, but he didn't reach round 2 because it wrote too much comments.
Another question from me. If you have to name only a resource online or a community to go and train from scratch to become a world-class champion, what would you name?
So unfortunately, I don't know any specific community with Python. One of the reasons I asked if there was anybody from Italy, because I would like to know someone else from Italy. So you are the only one. And the problem is, what works is local communities, whatever the language, or language-specific resources. In Python, there's nothing specific. The biggest community is Top Coder community, but they don't have Python. Not sure, there are a couple of other communities. The Top Coder is this one, Top Coder. There's Project Euler, which is not, I'm not sure if they have a community, but it's a lot of practice problems. Then there is Sphere and Light Judge, that also it's you can do a lot of practice. You have points, but I'm not sure if there's a big community because it's an old project. This instead, in Top Coder, they do weekly competitions. The problem is that they only accept C++, Java, C#, and whatever, but not Python.
Thanks.
Yeah, sorry, just one question. So there is, it's probably me that I haven't really understood well that like the biggest difference between like small, large, and data set. I'm saying if something works and is efficient on a small data set, why would it not be efficient on a large data set?
Okay, it's actually the reverse. You have 2 sets of limits for the small and the large. So you know that the small will actually be smaller, so you may skip some of the optimization. Or if you thought enough tricks and algorithms to solve the small, they might not be enough to solve the large. I'll show you another very nice problem. By the way, the biggest resource is actually the Google called Gem site, because they have a lot of practice problems, there are all of those, and they give you the solutions, there is the analysis, it's really great. So I think, let's see, round 1A. No. 1B. No. No, it was not 1C. Done. Qualification round. Fair and square. Oh, this one. Now, fair and square, it's okay, they describe something, what you want. It's something about palindrome numbers. I don't know, but it happens quite often that the problems are about palindrome numbers. And then this was quite strange. They had a small and too large. Small, it means you know if it's wrong. Large, it means you will not know if it's wrong or correct until the end of the summation. They had 10, 35, and 55 points. And here are the limits. You have some stuff that go up to 1,000 or up to 10 to the 14. Okay, 10 to the 14, it means you have to think something different. And then some of the numbers can go up to 10 to the 100. And here, you have to think something completely different. I solved all of them. I was very happy. This was really nice. And the trick here is that you can compute something that is only up to the square root of this, and then you can just look at stuff that are on the square root of that, so you get from 10 to the 100 to 10 to the 50, and then to 10 to 25. That is still too much, but then you realize that you don't need to check everything, and you can just look for 3 numbers instead of 10 numbers in some kind of stuff. So it's actually 3 to the 25, and 3 to the 25, it's doable. But not online. Not within 8 minutes. It took me 30 minutes, but I could pre-compute all the solution before downloading the large. So I pre-computed all the possible solutions. It took an hour. Then I had the solution, downloaded, cross-checked what I needed, and then uploaded. So the difference is limits really means you need to think different stuff. Different algorithms, different data structure, possibly different, a lot of stuff. Yeah. Other questions? Okay.
Thanks for having been with us with a really inspiring talk.
Thank you.